contaminated and is also just not available. And then some facts related to water. There are 780 million people worldwide that lack access to safe, clean drinking water, and that's about 10–11% of the population. In addition, 3.4 million people die every year from water, sanitation, and hygiene-related issues. So these are some maps that are kind of hard to see, but the top one is a global map of annual precipitation. And the red areas are regions that see very little precipitation, less than 25 centimeters annually. And then the darker regions, the dark blue regions, see more than 200 centimeters of precipitation annually. And then this lower graph here shows the percentage of population that has access to clean and safe water. The dark blue regions are percentage of population of 96 or higher. The light blue is between 83 and 96. And the yellow is between 65 and 83. The red is less than 65% of the population. And then the images over here on the right are global images taken by satellites, one in 1978, the other in 2012. And that just shows how much degradation there's been in vegetation due to lack of water. So our plan was to build a device that could harvest and capture the moisture from the humidity in the air. And we tried to use a solar absorption device that would generate a cold surface for water to condense on. And the goal was to make it entirely self-sustaining. So this is a diagram of the solar absorption. We unfortunately didn't get time to incorporate this with the project, but the basic idea here is that up here will be a carbon methanol solution, and when the sun hits that, the methanol will retract down into a chamber in here, and then when the sun goes away, the methanol will be pulled back up into the carbon, and that creates a pumping effect. And when the pressure goes down, the temperature will also go down, and we can use that eventually to form ice and have water condense on the surface that's holding that ice. So the immediate problems we ran into with this technique is that the water in the air went immediately from a vapor to an ice, and it completely bypassed the water stage, and for us that's just a waste of energy. So we needed to figure out a way to change our design to incorporate that better. So the solutions that we came up with was surround that device with a chamber full of water and use the water as a heat sink and partially freeze that water, and then the copper that surrounds that ice water solution would be a cold surface that water could condense on from the outside air. And then we also isolate and insulate that chamber so that we can control the airflow and things like that. And then after that, we began constructing and testing the designs. So this is kind of the schematic I came up with. We have the inner chamber here that would house the methanol, which is this piece right here to give you kind of a scale of what we're working with. And then there's a cone that'll be on the outer chamber here. And then this here is the outer chamber that we made. And it's hard to see, but down here we use tack welding to hold it together. And then after that, soldered the inside to fuse that seam. And then over here is Steve Jakowski forming the cone that goes on the end of this cylinder here. And that was actually really hard to do. We had to make two half cones and fuse those together. So that was a pretty difficult feat of engineering, but we were able to get it done. These are some more pictures. This is the cylinder all together. And then there's a polycarbonate cylinder that I was able to make and pop rivet together. And that acts as the insulation around it. And then here we have a fan, and we use the fan to control the airflow that goes into it. So this is a graph we took of the room temperature. I collaborated with a fellow student, Ben Cunningham. You'll hear from his presentation later. And so this is the room temperature we took during the room. We have the temperature in Celsius along the y-axis and the time it took in hours along the x-axis. And as you can see here, the temperature kind of spikes, and we believe this is from we started the testing at night around 4:30 or 5 o'clock, and we're assuming that in the evening and over the night the university turns off the air conditioning, so the temperature did go up a little bit. And then this is a graph of relative humidity in the room. Again, Ben helped me with this calculation. So we have the relative humidity in a percentage on the y-axis, and time again in hours on the x-axis, and the humidity drops throughout the same time period, and we believe that is again because the temperature went up, the humidity is going to drop a little bit. And based on those two graphs, those two numbers, we were able to calculate the dew point. And the dew point is the temperature in Celsius at which water can be condensed. And so again, we have temperature in degrees Celsius here, time in hours along the x-axis. And that range, it started at about just under 10 degrees and then dropped down to about 8.5 and then crept up again. This here is a graph of surface temperature of that large cylinder with the cone on it. And again, temperature in degrees Celsius on the x, time in hours on the y. And as you can see here, based on the last graph, this is the dew point in temperature, and this is surface temperature that goes to about 11 hours. We're well within the dew point for the time of harvesting, because if this is out at night, that's when the ice will be formed and the harvesting will be occurring. Excuse me. So this is just some of the thermodynamics of the system, and this basically explains that the total energy we have available right here is almost 3 million joules, and then the total energy it takes to convert 1 kilogram of water from vapor to a liquid. And with our system, we should be able to eventually get around 1.29 liters of water harvested without any additional moisture from fog. These are the results we got. So I put in 2 liters of water and 7 kilograms of ice, and that was to simulate the solar absorption device because we didn't have time to incorporate that. And when I had the system insulated with no airflow at all, I was only able to get about 5 milliliters of water. And that's because as all the moisture inside the chamber was condensed and harvested, the air became completely dry and there was no more water available to condense and harvest. And then I insulated it and turned on the fan and controlled the airflow and harvested between 50 and 55 milliliters. And then uninsulated, just having it sit in the room, I was able to harvest between 95 and 100 milliliters. And I believe this discrepancy is because the fan was blowing at too high of a speed and it was evaporating the moisture before it could be harvested. And then, so the features of the project are to build and incorporate the solar absorption technology, as well as change and analyze the different airflow ratios. And then we also have equipment from the engineering department to have a solar panel and a battery using a charge regulator, and we can use the battery to run the fan, and then that would help it be entirely self-sustaining. And then new tests, different designs, possibly using copper wool to surround the cylinder would help slow down the air and let the moisture get condensed out of it before exiting the chamber. And I'd like to thank Dr. Qualls for all of his advice, and then Stefan Jakowski. They really helped me build all of this copper material. Without them, I couldn't have gotten this done. And then Ben, Hunter, and Kevin for all their advice on different engineering designs. And then my family for all their support through these 5 years of school. Questions?
You mentioned producing water, so what humidity levels could this work? Because a lot of the areas are desert.
Right. Theoretically, as long as there's humidity in the air, it should work. Obviously, regions with higher humidity levels would see better results. But if there's any moisture in the air, it theoretically should work. So.
This experiment was done in the lab.
Yes, that's also true. It was done in the lab where, again, the temperature and humidity is controlled. If it were to be done in an outdoor environment overnight where the temperature drops and the humidity rises a little bit, we'd probably see better results. But I just didn't have time to get to doing experiments outdoors.
Any more questions?
So this would be ideal for like Haiti or in a tropical
Yeah,
environment,
an environment
where they have
that
water, fresh water shortages and problems.
Yeah, and environments that are high in humidity, it would also be very helpful for.
I think it's a really neat project, and it's good socially conscious project as well. So let's